This research is about finding new solvation radii for the CPCM model with nitrogen-containing molecules, which we'll discuss later on what this means. Solutions are mixtures of both a solute, a molecule that dissolves or breaks apart into individual atoms, and a solvent, the molecules that dissolve the solute. Solutions are important in our world because we would not be able to live without them. Many chemical and biological events in our body and cells happen in water, which is a solvent for many reactions. Now let's say, for example, that this is our solution. The solute goes into our solvent and dissolves, the process known as solvation. However, things need to happen before the solute interacts with the solvent. The solute needs to break through the surface of the solvent. The solvent breaks bonds between each other to form a cavity for the solute to reside. Then the solute equally repels and attracts the solvent while in the cavity, which we'll explain later. These four steps contribute to the sum of energy for the solute in the aqueous phase. The difference in energy between the solute in the gas phase and the solute in the aqueous phase gives us the solvation energy. There are many reasons to model solvation, with the most important reason being that experiments just take too long to conduct. It is also difficult to measure the energy of solvation when the solutes are too big or when the reaction happens way too quickly. So how do we model solvation? First, we need to represent the solute in our model. We do this by using quantum chemistry, which is a branch of chemistry that studies the physical properties of molecules as well as give information on their energy and structure through a series of equations and theories. But it takes an extended period of time to calculate through a computer. So how do we model the solvent? If each solvent molecule were to be calculated through quantum chemistry, it would take more than our lifetime to model the solvent. Therefore, we completely get rid of any solvent molecule and have the solvent behave as one, as shown in the implicit solvation model, and replace them with an electric field that surrounds the solute. This field has a charge and behaves like water, but without any information of its physical structure. This allows for faster calculations of the solvent. In this model, we can also see the cavity, which is defined as the space between the solute and the solvent. There are many types of implicit solvation models, but the CPCM model has our solute inside the cavity surrounded by the electric field. Going more into the cavity, you can imagine each atom having a sphere around it. This is known as the solvation radius. The inside of the solvation radius doesn't contain the solvent. If you were to remove the set of solvation radii in a molecule, one can imagine it as a cavity. The smaller the cavity, the stronger the interaction between the solvent and the solute. A molecule can have a different size radius for each unique atom measured in angstroms, making up a radii combination. The shape and size of the cavity define the radii definition, which will be the focus of our research. A previous graduate student from Loras, Sloan Newsel, decided to use 389 solutes, with 111 being positively charged and negatively charged, to construct a CPCM model using these three existing radii definitions that accounted for each atom having an individual solvation radius. In this table, we see what sizes were used for each atom and for each radii definition. She performed the experiment to calculate the solvation energy and then used that to find the difference between the experimental value, known as the error. A low average of error means that the model can replicate the experimental solvation energy well. What she found was that it was difficult to accurately represent solvation for both neutral and charged solutes. These radii definitions, however, weren't designed for solvation modeling, so we decided to use new solvation radii sets. The overall goal was to create new solvation radii combinations with the addition of nitrogen-containing solutes. There are two things to achieve when doing this: finding the best radii combinations for all solutes, and then finding the best within each type of solute. In our research, we used 565 solutes, which consisted of 475 neutral solutes and 90 charged solutes. Now, using a wider range of solvation radii, there are a total of 420 radii combinations for each solute. What we found was that for all solutes, the best radii combinations were when oxygen was at 1.4 angstroms and hydrogen was mostly at 1.1 angstroms. When looking at how many molecules could not replicate the experimental solvation energy well enough, known as failures, we see that two combinations highlighted performed best overall. At each individual type of solute, we see that the radii combinations performed best when they were large for neutrals and cations and small for anions.